In this video, I'll teach something called the proof by cases. Now, when you think of proof by cases, always think of two things, okay? Now, you wouldn't get they'll tell you to prove by cases. You have to make that, basically that decision. But if you look at the statement, if n is an element of integers, then n squared plus 5n plus 3 is an odd integer. Now, how do you start this equation? Because if n is an element of z, means it's all numbers such as minus 1, 1, and 2, and it goes on to infinity and negative infinity. So at the end of the day, how do you represent all these numbers? If it's even numbers, we can represent it as 2k. If it's odd, we can represent it as 2k plus 1. But integers, we can't represent integers as in just one thing, okay? So we have to split it. If we have a case where n is even and then a case where n is odd, then that means I'm covering everything, every single integer. Think about it. If n is even, it'll cover, it'll cover basic, think about it, all the integers, right? Minus 5, minus 4, minus 3, 2, 1, 0, 100, 9. If I cover all even of it and then all odd of it, it covers every single integer in there in the universe, right? So that's basically what is proof by cases, when you need to state two cases in order to do the proof. So firstly, we write proof. Now they're telling you over here if n is an element of integers. So let's say the first thing we do is even, so then we'll do odd. So suppose n is, so first we'll do even. Now, always when you suppose something, you say, so suppose n is even, then n is equals to 2 something, so 2k plus 1. So remember, we can use any letter, but I'm going to use 2k plus 1. So 2k plus 1. And then you have to say what is k, because you put k. So k is an element of integers. Now let's do the proof. So then n squared plus 5n plus 3 is an odd integer. So you made n equal to 2k plus 1 because that means n is even. So now put 2k plus 1 in this equation over here. So it'll be 2k plus 1 all squared plus 5 into 2k plus 1, because we're just representing, basically placing n as 2k plus 1 plus 3, and now we simplify. Now when you come to this, you'll simplify, you'll get to this, but somehow we have to show that it's an odd integer, so it'll be 2 times something plus 1. Now if I just put, now there's a common factor here which is 2, over here it's 2, but here how do you make this, basically how do you get 1 by itself? So instead of writing 9, we can write it as plus 8 plus 1, because that's 9, because now plus 1 matches with that, and now 8 you can take out 2. So if you take out 2 from here, you're left with 2k squared plus 7k plus 4, and then outside the bracket it'll be plus 1, and there we go, we prove that this is odd. Now anytime we go here, we say 2 times something in brackets, so like 2z plus 1. Z is a letter, any letter you can put, then you can say where z is an element, oh sorry, not element, z is equals to, so z is equals to this whole bracket. So I'm not going to write it, but put the whole bracket, which is an element of integers, right? And therefore you prove that it's when it's even, this will be odd. Now let's prove if it's odd, because remember there's two cases. So you rewrite this whole thing down, okay? I won't write the whole statement, but the whole statement down like this, just that instead of even you say odd. And then let's see, suppose n is even. Wait. Over here I actually proved that n is odd. So this is even, that's wrong. So what we did over here was, yeah, 2k plus 1, that's odd. So we actually did odd first, which is fine. You can do odd or even first. Doesn't really matter, right? So that what we did was odd. So it's fine. Now we'll do even. So, okay, so odd. So now we have to do even. So let's see. Okay, so let's do even. So remember, this is not even, this is odd. So if we do even now, we do the exact same thing, but we say n is equal to 2k. So suppose n is even, then n is equal to 2k. So you must write that. Now to do the proof, if n is equal to 2k, you just substitute 2k in n, like how we did here. So it'll be 2k squared plus 5 times 2k plus 3. And now we just simplify, right? So 2k squared, that will be 4k squared plus 10k. Now, just as I did over there where I said 3, we need 1 from 3. So we can rewrite 3 as plus 2 plus 1. We never change anything. Then we can take a 2 as a common factor. So you're left with 2k squared plus 5k plus 1. And then the 1 at the end, right? And there we go. We prove that this is odd. So we prove that when it's odd, putting an odd integer, it gives you an odd. We prove that if we put an even integer, it gives you an odd integer. So therefore we prove that any n is an element of n, any integer will give you an odd integer when putting this into this equation. And remember, I told you must write it's equals to like any random letter. So this, remember, you use another letter, don't use this letter. So here you can say 2m plus 1, and then where m is equals to this whole bracket, which is m is the element of the integers. Done. And I told you when you're done with the proof, put a square over here and color in the square. That means you're done. So proof by cases, you need two proofs to do it, and you'll see it in the question. It'll make sense what to do. That is proof by cases.